Good morning, everyone. Let's get started. So in the last class, we were discussing some examples trying to plot the capacity region for various channels. In particular, in an earlier class, we've derived the capacity region for a two-user discrete memoryless multiple access channel. We saw that the capacity region is the set of all rate pairs which satisfy the following inequalities. So R1 is less than or equal to the mutual information between X1 and Y given X2 and Q. R2 is less than or equal to the mutual information between X2, Y and Y given X1, Q. And R1 plus R2 is less than or equal to the mutual information between X1, X2. Yes.
Sorry to interrupt, sir. The screen is not in sharing mode.
Okay. Yeah, thanks for pointing that out. Is it visible now?
Yes, sir.
Yeah. So we saw that the capacity region is the set of all rate pairs which satisfy the following inequalities. So you have a bunch of three information quantities, mutual informations. The conditional mutual information between x1 and y given x2 q, x2 and y given x1 and q, and x1 x2 and y given q. All right, and so if you can find so if R1 and R2 satisfy these three inequalities for some joint distribution PQ, Px1 given Q and Px2 given Q, then that rate pair is achievable. All right, and for the Gaussian channel, so note that for a given Q, if you fix a particular Q, then each of these represents a pentagon, right? And but on the other hand, for more complicated distributions, I mean, once you take the convex combination, or in other words, you vary the distribution PQ, this rate region, the set of all rate pairs satisfying this, could be some complicated looking convex set. Right? But at least for the case of the Gaussian MAC, this turns out to be just a simple pentagon. All right. So in this class, we'll see an example of maybe a binary channel and a binary MAC, a binary input, two binary inputs and one binary output. And we'll try to at least numerically evaluate the capacity region. Okay, we'll try to plot the capacity region. And all we'll be using are these information inequalities. Right? So our goal will be to evaluate all of these points and then get a plot and see what the capacity region looks like. Okay. So any questions before we proceed? Okay. So let's take an example. So first, we need to write sort of so in this class I'll write a Python program to plot these points. I'm going to do it kind of on the fly, although I have some helper functions already. So let's get down to it. I will stop presenting this and instead share the window of a Jupyter notebook. Okay, so first, before we even sort of try to evaluate the rate pairs, we need some helper functions to compute various mutual informations, right? So we need to compute certain things. Let's make note of all of those. So we need to compute the mutual information. Perhaps. Is this a comfortable font to view? Do you want me to zoom in or zoom out?
It's compatible.
Okay, right. Yeah, so in case it's not, just let me know. Okay, so we need to compute certain quantities. One is the mutual information between x1 and y given x2 and q. And first need to I need to compute the mutual information between x1, y, and x2, q. I also need to compute the mutual information between x2 and y given x1 and q, and the mutual information between x1, x2, and y given. So first let's try to have some functions which do the following. I'm not going to write all of this down now because that will just take too much time. So one way, I mean, there are different ways to do it. I don't say that I'm doing it in the most efficient manner, but essentially to compute any mutual information, I need to compute a KL divergence. Right? So the mutual information between x and y is basically the KL divergence between p xy and px py. Right? The KL divergence between the joint distribution and the product of the marginals. So here I just have a helper function which helps me compute the KL divergence between any two distributions. Okay, so that is what this does. So this is going to be compute the KL divergence between two distributions. It looks a little more complicated because I'm just trying to take care of all the edge cases. So when some of the, when either p of pxy is equal to 0 or pxpy is equal to 0, we need to be careful in evaluating the KL divergence, but otherwise it's just the summation p of I log p of I over q of I, right? So you can implement this function in your favorite technique, but here is one way to do it. Okay, so now that I have a module which computes the KL divergence, I need some modules to compute these mutual informations. So given need to compute the mutual information terms, and what should the inputs for these be? I need to compute these quantities, and I know that the distributions have a certain structure. So I have a PQ, and then I'm also given, I have a probability mass function on Q. Then I'm given Px1 given Q and Px2 given Q, and of course I'm given the channel which is Py given x1, x2. Okay, so these are the inputs, and my outputs will be the following. So I1 is what I call the mutual information between x1, y, and x2, q. I2 will be the mutual information between x2 and y given x1 and q. And I12 is what will be the mutual information between x1, x2, and y given q. These are the three quantities that I have to evaluate. right? And okay, so this takes a little bit of computation, so I'll spare the details. I've already written a function to do this. And I'm just going to use it as it is. Okay, so note that this whole block essentially computes these three quantities. So the inputs are p of q, p y given x1, x2, p x1 given q, and p x2 given q, and it outputs three things. One is this mutual information, the other is this mutual information, and the third is this mutual information. Right? And the rate region is, so a rate pair is achievable if R1 is less than this, R2 is less than or equal to I2, and R12 is less than or equal to I12. Right? Okay. So this gives me one set of points. Right? So the output is basically this. Okay, so this is what my function returns, and I'll just have you believe me that this is indeed computing it correctly. Okay, so we have a block. So this function computes these terms. All right. Okay, so let's maybe fix some particular channel and then try to evaluate what this turns out to be. So first, for that, I need one particular channel. Okay, I'll assume that my alphabet, the alphabet for everything is binary. All right, so the alphabet for x1 is binary, alphabet for x2 is binary, for y is binary, and q is also binary. Right, so it's basically a channel where you have two inputs, x1 and x2. So there are two bits sent by two users, and the output, the receiver also observes a single bit in every channel use. Right, and q, remember, is the time sharing random variable. Okay. So I mean, there are different ways to generate p y given x, but let's say that I generate one randomly. So I generate one point. So I generate one particular channel randomly. So this corresponds to one particular p y given x. Let's generate one and see what it looks like. Uh, we should do it. So this is basically my channel. right? So when x1 equal to 0 and x2 equal to 0, y is equal to 0 with probability 0.88, and it's equal to 1 with probability 0.11. When x1 equal to 0 and x2 equal to 1, then the output is equal to 0 with probability 0.79 and equal to 1 with probability 0.204 and so on. So I'm just generating a bunch of numbers. So this gives me one particular channel. Right? So basically, to define the channel, I need 4 PMFs for y, right? One for x1, x2 equal to 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So far, so good. Any questions so far? Yeah, I'm randomly defining a channel. Now, you could look at one specific channel if you wanted to, but again, that's. But for now, I'll just look at a random channel. Okay, and this is the channel that I'm going to fix. So the conditional distributions are given as follows. Okay, so far what I've done is I've generated a random channel, a random binary MAC, and I also have helper functions which compute all the 3 mutual information terms that I need in order to compute the rate region. Okay. All right. So now let's maybe try to compute these forms. Okay. For this channel, let's take some px1 and px1, px2, and try to compute. Try to see what the pentagon looks like. Okay. So compute fusion for px1, px. Okay. Okay, so let's say that px1 given q is something. So it is so px2 given q. So, but these need to be valid conditional PMFs for each Q. So I need to normalize. So let's do that. So px1 given q is the same thing divided by. I'm just normalizing. Right. Similarly, px2 given q also needs to be normalized suitably. So this gives me a px1 given q and px2 given q. Now I want to plot a pentagonal region, so I'll just fix q equal to 0 or 1. Okay, so I'm just going to look at a particular px1 and pxq, and one way to do that is by saying that pq is just deterministic. Right? Instead of looking at a convex combination of 2 regions, I'm going to get one particular PQ. So maybe do it separately. Okay, so I've generated a px1 given q and px2 given q. Let's look at pq equal to this, and using this, so now I have a particular pq. I have everything defined. Now let me just call this function to get the three mutual information terms. Okay, so I1, I2, I12. So this is the mutual, the ix1 y given x2 q. This is ix2 y given x1 q, and this is ix1 x2 y given q. Okay, so let's compute these points. And maybe we also print it out. I2, I1. So I get some points. So it's so the first mutual information is 0.03, the second one is 0.06 bits, the third is 0.09 bits. Okay. Okay. All right. So now these correspond to these mutual information terms. Remember that if I want a rate pair, then R1 should be less than or equal to I1, R2 should be less than or equal to I2, and R1 plus R2 should be less than or equal to I12. Right? So if I have, let's say, so I evaluated these three terms, I1, I2, I12. And you know that this corresponds to some pentagonal region, right? For a given I1, I2, and I12. So how many points do you need to find this pentagon? And okay, fine. I mean, do you really need 5 points to describe the pentagon? You already know what some of the points are going to be, right? So okay, so let's say 5 points. So I know I1, I2, and I12. What are the 5 points going to be?
Two corner point we need to know.
Correct. So the 2 corner points are all what we need, and let's say, so what are the corner points going to be?
Ix1 given y and Ix2 given y. PQ turn
Is it going to be okay? So here I have these things, right? So tell me in terms of I1, I2, and I12.
Okay. I1 and I2.
I1, I2 will. Are you sure that's going to be a point?
No, that is not point. Yes.
So corner points will be I1 given 0 and I2 given 0. Like they'll be with respect to the axis, x and y axis.
Okay, so that will be 2 points, but those are not really the corner points that we are interested in, right? I mean, sure, that's true. You're right that those are going to be 2 points of the pentagon, but they're straightforward points. I also want to make use of I12, right? So in some sense, I need to find out what the base of the pentagon is in some sense. Right? Although I'm looking at an inverted pentagon. So let me instead present my notes. That will make it easier. Right. So note that these are. So this is going to be. So this is my I2. This is going to be my I1. Now I need to find out, so you're right that this point over here is going to be 0 comma I2. This is one point. This point is going to be I1 comma 0. So that's good. This point, of course, is going to be 0 comma 0 always. Now I need to find out what these 2 points are in terms of I1, I2, and I12. Right? So this line is going to be R1 plus R2 equal to I12. Right? So how will you evaluate these 2 points of the pentagonal region?
So this rightmost point will be I x1 y given y2 and
That's fine. Agreed. But so I've so all that I've computed are I1, I2, and I12, right? I want to plot this numerically. Remember.
I1 and I12, this point will be.
This will be I1 and it's not I12, something else. So note that this is R1 plus
yes.
R2 equal to I12, right?
So this will be I2 minus I12. This gap.
The other way around. It's going to be I12 minus
I2.
Are you sure it's I2?
So if
I1,
compute this one.
right? So you know what R1 equal to, right? In this line, R1 equal to I1.
Yeah, yes, got it.
Correct. This line is R1 plus R2 equal to I12. So R2 will be, so you have R1 plus R2 is equal to I12. So R2 is going to be I12 minus R1, but R1 is equal to I1. So it's I12 minus I1. So similarly, what is this point going to be?
I12 minus I2 and I2.
Exactly. I12 minus I2 and I2. Right? So having computed 3 points, three values, I1, I2, and I12, I can get 5 points on the rate region. Right? 0, comma I2, I12 minus I2, comma I2, I1, comma I12 minus I1, and 0, comma 0. All right. So let's go ahead and try to plot this. So I'll go back to my code. Share. So my corner points are going to be, right. So the points are, of course, I'm going to have 0, comma 0, and then I1, comma 0, I2, comma 0, 0, comma I2, 2, and then I have I1, comma I12 minus I1, and I12 minus I2, comma I2. Right, so these are the 5 points which are going to give me a particular pentagon. Okay, so let's try to collect all of these points in one go. And so let's let me call this I 2. One point is I1, sorry, I1 comma 0. Another point is 0 comma I2. I1 comma I12 minus I1, and the last point is I2 I12 minus I2 comma I2. Okay, so let's try to plot these. And zero. One. Okay, so this gives me these points, right? So this is 1 point, 0 comma 0. This is another point in the pentagon, and these give me the two other corner points of the pentagon. Right? So basically, the line bounding these 5 points corresponds to one particular rate pair. Sorry, so the achievable rate region is clearly contains this particular pentagon. Now this is for one particular value of px1 and px2. Correct. So let me just change this. So let's keep this as it is. Okay. Yep. So I'm going to keep it like this, and I'm going to say that just going to change this to 0, comma 1. I'm just going to change the px1 given q and px2 given q, and I will compute this. I get some other set of values for I1, I2, and I12. Okay, now I can do a similar exercise. I can plot the same thing, and I'm going to get another set of points, right? I've just changed the distributions px1 and px2, and I've evaluated the mutual informations. I get another pentagon, right? Just by changing the input distribution, I get another pentagon. Okay, so this is achievable. This pentagon is achievable. This pentagon is also achievable. So I need to find, so certainly the convex combination of these two pentagons is also achievable. Right? In particular, if I try to maybe plot all of these together, then I would get something like this. Let's try to do it. Okay, I'll define something else. So rate pairs is rate points. Let me have a copy of rate points in this. So let me make my job easier. I ultimately, what do I want? So I want to see what it looks like for different PQs, right? So I'm going to fix a PX. I'm going to fix a PY. I'm going to fix a PX1 given Q, PX2 given Q. The channel is obviously fixed. And now all I'm going to do is vary Q. So it's basically time sharing, right? So time sharing between two pentagons, and I want to see what that time shared region is going to look like. So let me define another function. Add 8 points, and this is going to essentially compute the following. So what do I want? I just want to add more 8 points, pentagons, for a new set of distributions. So this rate pairs is some set of rate pairs that I've already computed, some corner points that I've already computed, and I'm going to add more and more corner points by varying PQ, and PX1 given Q and PX2 given Q. So this will compute this, and let me see. So okay, so for this, I'm going to get one set of rate pairs. I've already computed one set of rate pairs. Let me compute another 0. I haven't defined rate pairs yet. Let's see. Okay. Okay, so this gives me one set of points. That is good. Okay. Okay, so it looks like this pend is changing the shape of my rate point. So let's try to correct that. So here's just a hack I'll do. I'm just going to increase. So essentially, I already have computed some set of rate pairs, and I need to add 5 more pairs, or just 4 more pairs. Right. So let's try to do that. I've defined this as B. So let's find the size of rate pairs. And just add more points. Okay, plus I'm adding 4 more points. This is two. Okay, so have these. So it's fixed. So, okay, sorry for the little bit of confusion. So essentially what we're doing here, so we've computed a set of rate points, right? So this function is computing those 5 points of the pentagon, essentially these points, and I'm just appending the new points for a new PQ, PY given X, PX1 given Q, and PX2 given Q. I'm computing a new set of rate points, and I'm adding those points to this particular array. Right? So I'm given a particular array of points, and I'm just adding those points to the array. Okay, so I've done this for one particular PQ. Let me do it for another PQ. Okay, so 0, 1. All right, so I get a bunch of points. Right, let's try to plot all of these together. Okay, so this is basically one set of points. So corresponding to one distribution, I have one pentagon which would look something like this. It's defined by these 5 points, and for another distribution, I have another pentagon which corresponds to this, right? And at least in this case, we see that there's one pentagon which is subsuming the other. So it includes the one pentagon is bigger than the other. So if you look at the convex combination of these two, you would just get the bigger pentagon, right? But now I can keep varying Q, right? So I can change Q to something else and then try to find out what this is going to be. So let me take some other PQ. So maybe 0.5, 0.5, and try to add these points. So I'll get some other points. It actually turns out to be this set of points over here, and similarly I can vary over Q, and I'll get different sets of points. All right. Now, what I can do is something better. I'll vary over all possible PQ, PX1 given Q, PX2 given Q, and see what the set of points are going to look like. Okay, so let's generate maybe maybe 1,000 distributions and compute rate point. So $1,000. Let me do the following. I'm going to generate a random PQ, PX given Q, and PX1 given Q, and PX2 given Q. So I'll generate a random PX1 given Q and PX2 given Q. X1 given Q and P of X2 given Q. And I'm going to generate a random PQ. P of Q, and use this to add more rate points. So this is, I'm going to add more rate points. And finally, let's just try to plot and see what that looks like. Right, so I've just varied over a whole bunch of Px1 given Q and Px2 given Q, and I get, so this is sort of a scatter plot of all the points which are achievable, right? So the convex hull of this is going to be my actual capacity region. Right? So I can increase the range, right? So from 5,000, I can maybe 1,000. So I generate 5,000 different distributions, and then I try to plot and see what this looks like. Okay, so something went wrong. Maybe there are too many points. So let's reset. Okay, yeah, so I do get something. It's just a little slow. So you see that it's a convex set, but it's not really a pentagon, right? It has this sort of curved structure over here. Right? It's gradually moving, but it's definitely not pentagon shaped. Right? So in general, these rate regions can look quite complicated. And again, there are different ways to plot this. But even for a simple two-user discrete memoryless multiple access channel, computing the actual capacity region is not a straightforward task. You can do it numerically, but note that this was just a simple binary input, binary output multiple access channel that we considered, and even here, it's fairly complicated to compute the capacity region. So for more general channels, it can get harder. And in particular, if the alphabet size grows larger, then the number of points that you will need to generate can be larger. So you need to generate more in random distributions to get a fine enough structure. And this is only for two users, right? We only looked at two transmitters and one receiver. For three transmitters, the capacity region is not going to be a graph. It's going to be it's going to be a three-dimensional region, and that can be, again, we can't even plot that, right? You can do it, but it's harder to visualize that. That is also going to be some kind of convex three-dimensional object, but it's hard to say what the shape of that is going to be. Okay. Any questions? So in fact, you can do slightly better than this. I mean, here I'll just put a scatter plot, but you can actually plot the convex hull of these points. There's a function in SciPy. It's called convex hull. So it gives you the convex hull of a bunch of points, and you can plot it. So for example, let me just reduce the number to 1,000 here. That makes it easier. That gives me some points, and using this, I can find the convex hull. Let's try to do this. And so this is what the convex hull is going to look like. Right? It can get fairly complicated very easy. So we just took a random channel and then we plotted this. By changing the channel, you'll get another capacity region. Right? So any questions? So I will post this code on Piazza. You can take your time and go through it. It's again not the most efficient or the simplest way to implement it, but it's one way. Right? So it can be computed, but it requires a little bit of effort. Right? But yeah, so in general, for any 2-user Mac, discrete memoryless multiple access channel, you can compute the capacity region in this manner. And even if you have, let's say, a continuous alphabet channel, you can always quantize. You can quantize the alphabet and then plot an achievable rate region, because for every quantization you get one achievable rate region. It's only by letting the quantization to be finer and finer that the achievable rate region will actually tend to the capacity region. All right, so if there are no questions, then let us stop here. We'll continue in the next class.
Sir?
Yes, Rohit.
Not about this, sir, like about the final presentation and project.
Yes.
I did
So
not
just
get
one sec. Let me just stop recording since it's not to do with the class.